So now that you're taking a logic course alongside a programming course, they're very interrelated. The first thing I would suggest you do before you fix any compile time errors, sometimes they're there because there's actually something logically wrong with your program. And so stepping through and making sure that, you know, what you're asking it to do is accurate will actually save you a lot of time. So before you just add a semicolon, make sure you understand, you know, the ramifications. Really relevant, because it's part of the reason that we care about being able to prove something works, right? So we're talking about proof, and people think about proof from a mathematical standpoint, right? We prove things and we create new rules. Well, sure we do. It's a great thing to do. It's how we have many of the theorems that we'll look at through this course. But the reason it's really useful to us is that we can prove that by taking in this specific input, this starting from some premise, as we have done with our logical statements, we will produce a certain set of output. So we'll arrive at some conclusion. And so what we're looking at is, you know, when we're looking at implication, the antecedent and the consequent, or when we look at rules of inference, we talk about starting from some premises and drawing some conclusion. Proof is doing exactly that, and that's what a program does, right? We start with some input, some premises, and then we work towards some output. And so that's the motivation to why all of this matters, and the fact that we shouldn't be scared of this. We do it all the time. We just do it in a different way of thinking. So this is our introduction to proof, and we've talked about how to deal with valid arguments, and we're going to use those to sort of prove our point. So far we were looking at logical statements and one thing we hadn't done was then look to, well, what if we want to quantify things, and what would the rules of inference be when we're talking about quantified statements? So we looked at rules of inference where we saw modus ponens, where we said P implies Q and P is true, therefore Q, right? So hopefully we remember that we saw this in the last class. What if they're quantified? So what if we have something that describes all of the elements in a domain, right? And we see this all the time. So I have a simple example on the screen, but sometimes we want to say that something holds for all integers, or all real numbers, all negative numbers, all numbers greater than 3. And so sometimes our propositions are only valid for a domain, a range of numbers, times of day, students in a particular class. Okay, so for example, and this domain can be many different things, right? It could be all elements in database. And so maybe it's all students at Dalhousie. So for instance, if our domain is all the students at Dalhousie, and we say we're going to use X to represent those students. So X is a computer science student. We can create propositions like X is a computer science student, and M of X as X will take a discrete math course. And then we can have propositions from that that involve quantified statements. So we can combine those and say for all X, C of X implies M of X. So that means all students, for all students, if they're a computer science student, then they will take a discrete math course. Essentially, this is bringing it all back together. So now we're going to apply the rules of inference to our for all and there exists. And you remember the the A is upside down, right? And to remember which those symbols are, there exists. So the E is flipped. Okay, so for all and there exists. And so that's just saying for that proposition P, this happens for every possible element X in that universe of consideration. And this statement means there exists at least one for which that proposition holds. And so we'll look at examples of this. But we're going to use this in two very specific we're going to talk about instantiation and generalization when it comes to the use of for all and there exists in this context. Okay, so we're going to look at what that means. So, and we'll have this for both universal, the universal quantifier, which is our for all universe, taking the whole universe, and existential is the one that says there exists, right? So for the existential quantifier, we'll also have instantiation and generalization, which sounds like big words, but it's simple concepts, okay? We'll show you what it is. So the first is universal instantiation. And that says, given the premise that for all x, p of x holds, we can conclude, and I'll step through it slower, but just read it through first and think about what this could mean, then we can conclude that if C is an element in our universe, then P of C is true. Okay, I'm going to show it to you in the form that we'll think about this. This is the rule of universal instantiation. So this is taking these quantifiers and saying we can also create rules from them and learn, infer information from them. Okay, so what that says is that if our premise, so this is our premise, is that for all x, p of x is true, right? When we see it above the line, we say we're assuming this holds. And then we're going to draw a conclusion. We can draw some conclusion. So that's saying if it's true for everything, everyone in the universe, then if I pick any one person in that universe, it's true. Okay, so if I say for all computer science students, they will take a discrete math course, then if I pick any one computer science student, say Brent, then we know it's also true for him. Brent has taken a discrete math course. Okay, and if I pick any one of you because you're computer science students, we can say you will have taken a discrete math course. Okay, if this holds, if the premise holds, if it's true for everybody, it's true for any one person that I want to pick from that group. Right? It seems a little simple to even have to say that, but there are reasons that this matters in terms of how we prove things. So if we know we have the premise that it's true for the universe, if it's true for everybody, then we can say that if we pick anybody within that set, it must also be true for them. And then we can follow from that. And I'll show you examples of how that takes place. So then there's a counterpart to this, which is called existential instantiation. What's fun about discrete math is this concept there, it's true for everybody, then if you pick anybody in that group, it's true for them as well. That's a simple concept. The names are quite something, aren't they? So you can go to your friends and say, oh, yes, I understand existential instantiation now, and it sounds quite grand, even though the concept is really easy. So here's how simple it is. So there is an x where p of x is true. There exists an x in U such that p of x. What that says, we assume the premise is true. It means that there exists some element in the universe for which this is true. Then we can conclude that there is a C in the universe for which it's true. It's almost saying the same thing, isn't it? But what it's doing is it's saying there is absolutely one. If we say there exists one, then there is one, and we can find it. There is some C for which this is true. Okay. If it's true for somebody in the set, then we can find a person in the set for which this is true. Or if it's true for an integer, for some integer, we can find an integer. There is an integer C for which this is true. We don't know which one, and that's an important point here. Whereas in universal instantiation, it doesn't matter which element from the set that we pick because it's true for all of them. This one's a little bit different because it's saying there is a C for which this is true, which is not the same as saying pick any C and it will hold. We can say this will hold for at least one element. So instantiation, just as we tried to think about words to remember why, we would call this universal and existential. Universal is about the universe, the whole thing. It's true for everything in the universe. Existential means there exists something. Instantiation is about finding an instance, one element within that set, and saying something about it, right? So when we talked about the universe, we said for everything in it, P of X holds. For all X, P of X holds. Then we said, okay, well, if we consider one instance, C, then P of C is going to hold for all of them. And with existential instantiation, now we're talking about the existence of something. There exists an element for which this is true. Then if we look at some instance C, we can find one instance where this is true. Okay? And the reason I point that out is the next word that we look at is generalization. And this is more about saying, if we can say something about an element, how can we generalize that to the whole population, or throughout the whole population? What can we say? So this generalization is about learning something in the small and then extracting it out to the big, right? Looking at the whole set, what can we say? So the first concept is universal generalization. So what can we say about everything, the universe? Okay, so now we're saying, okay, well, we can say that P of C is true for some arbitrary element C. So if I can say I've got an element C in the set, I don't know which one. If I can say it's true, if I can say I have a student in the discrete math course, and I can say something is true about that student without specifically saying I'm talking about Braden or Trent or Abhishek or Anna, right? If I don't specify who I'm talking about, but I just say it's a student from discrete math, and I can prove that something's true no matter who they are, then we can go further and we can generalize and say, well, if it's true for a student that I have yet to put bounds on, then it must be true for all students. And so if I can say, for instance, if I can show you that I can pick an odd number, x 2x plus 1, right? If I can show you that something is true of this, like 2 does not divide this number, then I can generalize and say, well, that's true for all odd numbers, because this representation could be any odd number. So this is another rule of inference, and this is going from something we know about one element in the set and then generalizing it to the whole group. So if I can say that P of C is true for some arbitrary element, then I can because it's, and I think what's important about that is arbitrary. And arbitrary just means it could be any element in the set. You're not defining that. And we'll see examples to show you how do you deal with an arbitrary element. So if P of C is true for some arbitrary element, then we can say, well, because C was arbitrary, because it's an odd number in my previous example, then it must be true for all odd numbers. We don't have to show as much if we just need to show that it's existentially true. So if we want to show that it's true for n element in the set, then we only have to find one. So if we show that P of C is true for some element in C, and that can be specific. If my statement is student X is from Botswana, right? If I want to show something about that fact, and then I find a student who's from there, is from Botswana, right? Then I can say there exists a student in this class that's from Botswana. If I want to say, if my proposition is student X is from Mexico, and then I find that Anna is from Mexico, then I've shown that I have a student for which this holds, so that I can conclude that there exists a student within our class for which this holds. Okay.